Have you ever looked down and really looked at the soil? Maybe you wondered why soil is red in some parts of the country, but boring brown or even whitish in mine. Soil is a very slowly renewable resource. Although many of our soils originated long ago, the forces that create them continue to operate. Some soils are hundreds of thousands of years old, while others just began to make their appearance yesterday. Soils grow, change, and develop. I'm Dr. DeBusk, and this video describes the soil formation processes. Soil is a collection of natural bodies of the Earth's surface containing living matter that is able to support the growth of plants. Soil varies across the landscape. In one area, it may be mostly made of decayed plant parts, whereas in another place, it may be mostly sand. It is not possible to learn everything about a soil just by standing on the surface. One must dig a hole to see what it looks like below the surface. Because a soil scientist cannot dig up acres of ground to study a whole body of soil, soil is divided into small parts that can be easily studied. This small body is called a pedon. A pedon is a section of soil extending from the surface to the depth of root penetration, measuring about 3 feet by 3 feet by 5 feet. This soil body can be studied, classified, described in a soil survey report, and used. A collection of pedons that are much the same is called a polypedon, which are mapped into units called soil series. How does a soil pedon form? Picture a section of bare rock that could someday become a soil pedon. In the process of soil formation, this rock is changed into a layer of small, tiny mineral particles with some organic matter mixed in. Weather and plants are the major agents responsible for forming soil from rock, and the process is called weathering. Physical weathering is the disintegration of rock by temperature, water, wind, and other factors. The photo on the left shows bedrock being fractured by physical processes. Physical weathering reduces particle size, does not alter the chemistry of the material. For instance, in cold climates, frost wedging occurs when water freezes and expands in rocks or in cracks in the rock, causing it to break apart. The alternate expansion and contraction of rock caused by heating and cooling cycles also stresses the fabric of rock. Both cause rock to fracture or outer layers to peel away. Rain, running water, and windblown dust also wear away at rock surfaces. Chemical weathering changes the chemical makeup of rock and breaks it down. A common process is dissolution, minerals dissolving in water. In hydrolysis, minerals react with the hydrogen that is in the water molecule, splitting the water apart. For example, the feldspar mineral orthoclase undergoes hydrolysis by replacing the sodium in the mineral with hydrogen, creating a new, softer feldspar. Other processes include hydration, where the water molecule joins the crystalline structure of the mineral, and oxidation reduction. Soil formation does not stop when a layer of young soil covers the surface. The new soil continues to age slowly and develops over thousands of years. Soil scientists state that 5 factors operate during the process of soil genesis and development: parent material, climate, life, topography, and time. One could say that over time, climate and living things act on parent material with a certain topography to create soil. Some have suggested that human activities might be named a 6th factor, because most soils have been modified to some degree by humans. Soil formation begins with rock, which supplies the parent materials for most soils. Before studying the 5 factors, let us look at the rocks of Earth's crust. The original source of most soils is rock, the solid, unweathered material of the Earth's crust. Solid rock breaks into smaller particles, which are the parent materials of soil. Rock is a mixture of minerals that, when broken down, supply plant nutrients. Geologists classify rock into 3 broad types: igneous, sedimentary, and metamorphic. Igneous rock, created by the cooling and solidification of molten materials from deep in the earth, contains minerals that supply 13 of the 17 plant nutrients. Igneous rock may be coarse-grained with grains and crystals large enough to see with the eye. Basalt is fine-grained. Darker colored igneous rocks tend to weather more easily and contain more iron and calcium. Granite is a hard, coarse-grained rock made of feldspar, quartz, and other minerals. Feldspar, a fairly soft mineral containing potassium and calcium, weathers easily to clay. Quartz, a very hard and resistant mineral, weathers slowly to sand. Most of the crust is igneous rock, but it is only 1/4 of the Earth's surface. Sedimentary rock overlays 3/4 of the igneous rock. Sedimentary rock forms when loose materials such as mud or sand are deposited by water, wind, or other agents, slowly cemented by chemicals or pressure into rock. Sand deposits can solidify to sandstone, a light-colored, coarsely grained rock. Loosely cemented sandstone weathers easily to release sand. Mud deposits form shale, a fine-grained rock. Limestone forms when calcium-rich grains of calcite settle out of ocean water. Many American soils are derived from sandstone and limestone. These soils are generally infertile and dry. Limestone is high in calcium and weathers easily to soils high in pH, calcium, and magnesium. Metamorphic rock form when igneous and sedimentary rocks are subjected to great heat and pressure. Limestone, which is fairly soft and gritty, changes to marble, harder rock, when subjected to heat and pressure. Sandstone changes to quartzite. Soils from metamorphic rock tend to look like the original sedimentary or igneous rock. Soil genesis is the process of creating soil from parent material. The description of soil origin earlier in the chapter was a soil formed directly from bedrock. Such a soil might form from the rocks in the rock cycle. These residual soils formed in place from the residuum of broken down bedrock are actually less common than soils of parent materials carried from elsewhere by such pervasive agents of transport as wind, water, ice, or gravity. Residual soils form slowly, as solid rock must be weathered first. Transported soils develop from already weathered material, so they develop more quickly. This figure shows parent materials of soils in the United States. Let us look at the agents of transport and the sorts of parent materials they carried. Parent material transported by ice is called glacial till. This parent material is found where glaciers have deposited material, such as in terminal or lateral moraines. Ice is a poor sorter of particles, and thus glacial till contains everything from the smallest clade-sized fraction to rocks, petals, and boulders. Glaciers left behind a distinctive landscape over much of the northern United States and Canada, often rich in wetlands, lakes, and ponds. Parent material transported by wind is called loess or aeolian. Wind is a good sorter of particles. Larger particles tend to bounce on the Earth's surface, while smaller particles are transported greater distances. Loess soils are important agricultural soils in much of Iowa, Illinois, and neighboring states. Dust blown from the Sahara Desert of Africa makes a significant contribution to soils of the Caribbean islands as well as Central and South America. Parent material transported by flowing water, streams and rivers, is called alluvium. Water is a good sorter of soil particles. Larger particles, that is sands, settle out of the water first, making levees or floodplains, and smaller particles, that is clays, settle out of the water last, making deltas. Thus, you tend to find sand-sized particles closer to the water source and clay-sized particles further away. Floodplain soils are especially important along the Mississippi and its tributaries, and along rivers that flow into the ocean on the east and Gulf coasts. Many important soils of California are from river alluvium. The term lacustrine classifies parent material transported by a lake. Water is acting on the parent material, and thus there is a high degree of particle sorting. Most of our lacustrine soils remain from giant glacial lakes that have since dried up, including Glacial Lake Agassiz of northern Minnesota, North Dakota, and Canada, and Glacial Lake Bonneville of Utah. When glacial runoff water ran into the lake, the heaviest materials were left near the shore, while the smallest particles were carried to the center of the lake. Lacustrine soils have flat terrain and, being poorly drained, can host rich agriculture with proper artificial drainage, but challenge the home and septic field builder. The term marine classifies parent material transported by oceans. Water is acting on the parent material, and thus there is a high degree of particle sorting. Many scattered soils of the Great Plains and the Imperial Valley of California are beaches of prehistoric seas that once covered the United States. Other beach soils are common along the Atlantic coastline and the Gulf of Mexico. All these tend to be sandy soils. Sounds like Florida, right? The term colluvium classifies parent material transported by gravity. Colluvium is made up of a heterogeneous mixture of boulders, rocks, pebbles, and soil from upslope areas. Thus, the degree of particle sorting is low. Sand and rocks collected at the foot of a slope is talus. These are common in areas with mountains, such as Arizona. The ash blown out of a volcano and deposited nearby or carried some distance by wind forms a chemically distinct, dark, and lightweight parent material called tephra. The mode of transportation is wind. Wind is a good sorter of particles. Larger particles tend to bounce on the Earth's surface, while smaller particles are transported greater distances. The Pacific Northwest, Hawaii, and Alaska are areas of the United States where such deposits are common. Organic soils, containing 20% or more organic matter, form underwater as aquatic plants die. Low oxygen conditions underwater retard decay of these dead plants, so partially decayed remains tend to pile up at the lake bottom. Organic soils are extensive in Minnesota, Wisconsin, Florida, Michigan, and Alaska. When climate is extremely complex, we are speaking here primarily of temperature and precipitation. Arid, semi-arid, and humid refers to climates that experience very low, and higher rainfall, respectively. Climate first affects soils, causing physical and chemical weathering of rock. Temperature affects the speed of chemical reactions in the soil. The higher the temperature, the faster a reaction. Chemical weathering in soils occurs mostly when the soil is warmer than 60 degrees Fahrenheit. Thus, in cold areas, such as tundra, soils develop slowly. In warm areas, such as the tropics, soils develop more rapidly. Another result of temperature is its effect on organic matter. Warmth promotes greater vegetation, so more organic matter is added to the soil. However, warm temperatures also speed the decay and loss of organic matter. Thus, soils of warm temperatures tend to be low in organic matter. In warm regions, warmth promotes dissolution of materials, so if climate is also humid, chemicals leach out of the soil more quickly. Warm climates also promote the weathering of clay minerals to forms that are less fertile. Soils of this piece of the Sonoran Desert near Phoenix are influenced by sparse vegetation and arid climate. Desert soils tend to be enriched in salts that would leach out of the soil in humid climates. In this diagram in the United States, it shows that the average organic matter increases to the east and north because of higher rainfall or cooler temperatures. Other factors also affect organic matter, like vegetation, which alters these trends regionally. Another effect of climate is on soil pH. Calcium carbonate accumulates in the western U.S., increasing pH, and humus accumulates in the eastern U.S., decreasing pH. Organisms that live in soils, such as plants, insects, and microbes, actively affect soil formation. The actual properties of a developing soil are influenced especially by the type of plants growing on it. The figure shows the parent vegetation of soils of the United States. Mineral soils having the greatest organic matter content form under grasslands or prairies. Grassland vegetation, mostly herbaceous, forms a deep, dense mat of fibrous roots, many of which die each year and contribute large amounts of organic matter to the soil. Indeed, most of the biomass of a prairie develops underground in the soil. This keeps their organic matter content high and the soil color dark. In a forest, much of the biomass grows above ground in the trees. When leaves fall or the trees die, the material falls to the soil where it creates a surface layer of organic matter that does not mix with deeper layers. As a result, forest soils have less organic matter than prairie soils and display shallower topsoils of lighter color. The type of trees also influences the soil. Compared to hardwoods, deciduous trees, softwood conifer foliage is acidic and resistant to decay. Therefore, their soils tend to be thinner, lower in organic matter, and more acidic. Deserts with very sparse vegetation have the least organic matter. Deep roots of deciduous trees extract ions from deep in the soil, leaving the surface horizon of deciduous forest soils enriched in ions. We tend to stress vegetation as the main living factor in soil formation, but other life impacts soil as well, such as burrowing animals that mix the soil, earthworms that create large, deep pores and speed organic matter decay, or nitrogen-fixing bacteria. Topography, or the soil's position in the landscape, influences soil development mainly by affecting water movement and soil wetness. Major changes in soil type can occur over very small differences in elevation and distance due to topography. 1. This soil developed on the hilltop, which is relatively flat. Therefore, the soil is relatively deep and well drained. It also received direct sun and is thus relatively dry, dominated by shrubs and to a lesser extent grasses. 2. This soil developed along the hill slope with a south-facing aspect. Soils are eroding due to slope, and thus there is relatively less soil development. This soil is dominated by grasses and to a lesser extent shrubs. 3. This soil developed along the toe slope, somewhat flat and still affected by its south-facing aspect. The soil is somewhat wet, as evident by the somewhat gray subsurface soil. This soil is dominated by grasses and some wetland plants. 4. This soil developed in the valley and is shaded by the northern slopes. Many soil materials, including mineral and organic matter, have eroded into this area. This area is low-lying and thus wet. A high water table is present. Thus, the soil profile is relatively thick and dominated by wetland plants. 5. This soil developed on the north-facing aspect. Thus, they are cooler temperature-wise as compared to the south-facing soils. These soils support coniferous trees, which deposit plant litter with an acidic pH. The litter accumulates on the surface and decomposes slowly. When it does decompose, it releases acid, which causes the breakdown and movement of soil materials out of the white upper soil and redeposits materials in the lower, darker soil. Soils change over time, undergoing an aging process. Initially, a thin layer of soil appears on the parent material. Such a young, immature soil takes as little as 100 years to form from well-weathered parent materials under warm, humid conditions. Under other conditions, it may take hundreds of years. Weathering of the young soil continues, and many generations of plants live and die, so the young soil becomes deeper and higher in organic matter. If there is enough rainfall, leaching begins to carry some material deeper into the soil. As soils age, biological processes tend to increase the nitrogen content, while leaching tends to reduce phosphorus. Thus, young soils tend to be low in nitrogen but high in phosphorus, while older soils are the opposite. Mature soils are generally productive, but as soil continues to age, they become more severely weathered, more highly leached, and often less productive. In general, as soil ages, it becomes deeper, develops distinct layers, and becomes more acidic and leached. Time zero for a soil usually begins when some dramatic events such as landslides, glaciers, or piling of mining spoil changes everything and resets the clock. Such events can happen at any time. Soils can erode away, be buried, or even become the parent material for a new soil. If soil factors change, the direction of soil development can be deflected into a new path. For instance, if forest invades prairie, the soil embarks on a new path towards a forest-type soil. We tend to think of soil development as progressive, that is, soil becomes deeper and more complex with more and better defined layers. But if the combination of soil-forming factors changes, soil can also regress, becoming shallower and less complex. Very old soils may have undergone repeated cycles of progression and regression. Humans may be considered just another living entity that modifies soil, but their action can be so rapid, dramatic, and different from other life that they may be considered a separate sixth soil formation factor. Very few soils have been unaffected by human activities. Effects may be as subtle as the deposition of air pollutants distant from any human habitation to as massive as earth moving during road construction. The latter resets the time clock for this new soil material to zero, and the earth moved by the machinery is the parent material for this new soil. Much of what people do to grow plants alters the soil, like cultivation or fertilization. Humans also enrich soils around them in phosphorus by fertilization and disposal of garbage. This effect is distinctive enough that archaeologists use phosphorus enrichment as evidence of early human habitation. Our system of soil classification also recognizes such enrichment in some soils. Soils change over time in response to their environment, represented by the soil-forming factors. Soil scientists have classified the causes of those changes into 4 soil-forming processes. Additions. Materials may be added to the soil. Some examples are fallen leaves, alluvium, and human-made materials such as air pollutants and compost. Deposition of nutrient-rich dust is a major contributor to the fertility of many soils. Losses. Materials may be lost from the soil as a result of such mechanisms as deep leaching, erosion from the surface, or gases filtering out of the soil. Translocations. Materials may be moved within the soil by leaching deeper into, but not out of, the soil by being carried upward with evaporating water, by being moved by animals such as ants or earthworms, or by other action that moves soil material around. Transformations. Materials may be altered in the soil. For example, organic matter decay, weathering of minerals to smaller particles, or chemical reactions. For example, some soils contain caliche, a hard subsoil layer cemented by lime. Its formation has been explained this way. Over long periods of time, lime-laden dust is deposited on the soil surface. Addition. It is leached downward by percolating water, translocation, and precipitates out as solid lime at some depth, transformation, where it cements a soil layer. This process requires the correct amount of rainfall, enough to translocate the lime downward, but not so much as to move it out of the soil altogether. Loss. Each of these processes occurs differently at different depths. For instance, organic matter tends to be added at or near the surface, not deep in the soil. Some material moves from high in the soil to be deposited lower. As a consequence, different changes occur at different depths, and horizontal layers develop as the soil ages. These layers are known as soil horizons, visible wherever the earth is dug deep enough to expose them. The soil profile is a vertical section through the soil extending into unweathered parent material and exposing all the horizons. Each horizon in the profile differs in some visible, physical, or chemical way from other horizons. The O horizon is an organic layer made of wholly or partially decayed plant and animal debris. The A horizon, called topsoil by most growers, is the surface mineral layer where organic matter accumulates. It is darker than the horizons below. Over time, this layer loses clay, iron, and other materials in downward moving water, a loss called alluviation. The E horizon, the zone of greatest alluviation, is very depleted in clay, chemicals, and organic matter. Because chemicals that color soil have been leached out, the E layer is very light colored. Many soils have no E horizon. It is most likely to occur under forest vegetation in sandy soils in high rainfall areas. The B horizon, or subsoil, is often called the zone of accumulation, where chemicals leached out of the A and E horizons accumulate. The C horizon lacks the properties of the A and B horizons. It is the soil layer little touched by soil-forming processes and is usually the parent material of the soil. The R horizon is underlying hard bedrock such as limestone, sandstone, or granite. It may be cracked and fractured, allowing some root penetration. The R is identified only if it is near enough the surface to intrude into soil. As soils age, they may develop more horizons than the basic master horizons. These transitional layers are identified by the 2 master letters, with the dominant one written first. Thus, an AB layer lies between the A and B horizons and resembles both, but is more like the A than the B. A soil layer can be further identified by a lowercase letter suffix that tells some trait of the layer. Now for an example. The photo shows the top 42 inches of the Clarion soil found in Iowa and Minnesota. Clarion is a prairie soil with a deep, dark-colored A horizon. The top 7 inches are a plow layer from cultivation, hence labeled AP. The thick A horizon extends below the plow layer and is divided into an A1 and an A2. The differences between them are not readily visible in this photo. This makes the total horizon 18 inches deep. At 18 inches, the BW horizon appears, a weakly developed B horizon. It is lighter in color than the A above, but darker than the C below. Again, there are two BW layers, hard to separate in this photo. At 36 inches, the C1 horizon begins and extends below the depth of the photograph to 52 inches. A C2 underlays the C1 at 52 to 60 inches. In this photograph, the C horizons are lighter in color than the B. This soil contains no E horizon because the soil forming factors here do not favor development of one, nor is there a R horizon because bedrock is somewhere below the zone they study. In conclusion, soils form from minerals broken up by the action of weathering and plant roots, and from the addition of decaying plant parts. Young soils continue to age, growing deeper, being leached by rainfall, developing layers, and changing over time. Over time, soil deepens and develops recognizable horizons, and may finally become severely weathered and highly leached.